So we've been looking at this reaction where we take a diene and treat it with acid, and we can generate those two products. And we can see those two products. We have the 1,2 addition and then the 1,4 addition. What if you want to only get one of those molecules? What if you want to select for the 1,4? Or what if you want the majority of your product to be the 1,2? Is there a way to do that? And there is. And the way to select one over the other is the use of temperature. So if you do this reaction at room temperature or elevated temperatures, your major product is going to be the 1,4 product. And this 1,4 product is also called the thermodynamic product. Now, why is it the thermodynamic product? Why do we call that? Because when we compare the two, we can see that the 1,4 product has a di-substituted alkene. There's our alkene, and we can see that it has two alkyl groups attached to it. And we've learned in Orgo 1 that more substituted an alkene is, lower in energy, more stable it is. And when you look at the 1,2 product, we see that this alkene is a monosubstituted alkene. It only has one alkyl group attached to it. So if we look at this energetically, what we're saying is the 1,4 or the thermodynamic product, which is going to be lower in energy than the 1,2 product. Okay. And the reason why, just to repeat myself, the reason why the thermo product is more stable because it is more substituted. Okay. Now, what if you want to favor the 1,2 product? Well, you can guess that we have to lower the temperature. If we lower the temperature and get it really cold, we are going to favor the 1,2 product over the 1,4 product. And the 1,2 product, because we are at cold temperatures, we call that, the 1,2 product is also called the kinetic product. The kinetic product forms at colder temperatures because that is the product that is formed the fastest. At elevated temperatures, the thermodynamic product is chosen because at higher temperatures, the reaction is under thermodynamic control. On cold temperatures, the reaction is dictated by kinetic control. And kinetics is how fast a reaction occurs. So at a cold temperature, this guy is going to form faster. Okay. Now let's take a look at an energy diagram to help make sense of this. Now this example right here has a little typo on it. So replace all the bromines in this with a chlorine. Okay. So we'll just replace all those with a chlorine. If we kept the bromines, the answer would still be the same. The bromines don't change anything. Okay. Now, I misspoke a little bit, so I want to correct this. So the kinetic product is going to be formed the fastest. Okay? And the kinetic product will be formed the fastest in hot temperatures or cold temperatures. Kinetic products are always formed first because they form the fastest. Okay? But I did say that in cold temperatures, the reaction is under kinetic control, which gives us this product right here. And when we have temperatures, the reaction is under thermodynamic control, which gives us this product. Okay? So what happens here? Okay? So at very cold temperatures, the reaction proceeds. Okay? And it goes through this high energy transition state. Now we're here at this intermediate spot. Now, under kinetic control, we can see that the energy barrier is in the blue line. The blue line is the kinetic pathway. How do I know that's the kinetic? Because look at the energy difference between the red and the blue. So if we were doing this reaction, we can see going through the blue pathway is going to be faster because it's easier to go over the blue hill versus the red hill. So because the blue hill is lower, it's going to go faster and give us this product. Okay? Under kinetic control or low temperatures, this intermediate does not have enough energy to get over the red energy barrier. So at low temperatures, the most probable option or pathway is the blue line because it's lower in energy and there's not a lot of energy being given to the system when it's cold. Now, contrast that to when the system is under thermodynamic control, which means we are adding heat to the reaction. What happens to that is at the very beginning of the reaction, there's heat, and we're going to follow this pathway. And which hill is easier to go over? Clearly the blue one. So we, even under thermodynamic control, we're going to get a lot of product that is going to give us the kinetic product. But here's the kicker. Why is this one favored under thermodynamic control? That is because this product right here now has enough energy due to the heat being added to go back. And so you can get a lot of this kinetic product to reverse back to this intermediate and then go through the different pathway, the thermodynamic pathway, to get to the 1,4 product. So when we're at cold temperatures, this product right here does not have enough energy to go in the reverse and go back. That hill is too tall to climb. It cannot go backwards. But when heat is applied, then it has enough energy to go back. And when it goes back and it's reversible, eventually the majority of the molecules are going to end up as the 1,4 product. So typically, when a reaction is under kinetic control, it's going to be irreversible. And when a reaction is under thermodynamic control, the reaction is reversible. Okay? So that's what temperature does. When you increase the temperature, it makes the reaction reversible, which then allows the molecules to eventually get to the lower energy, more stable thermodynamic product. Okay. So this slide right here is just a summary of everything that I just said. Now let's delve into another reason why the kinetic product gives us the 1,2. And it has to do with this idea called proximity effects. So when you do the first step in the mechanism and this chlorine leaves, you see how it's right there? It's already really, really close to the carbon that it's going to attack. Because you see how where it is in three-dimensional, or where it is in space? It's right there. That chlorine is really close to that carbon. And when that chlorine atom becomes a chloride, it's already there, and then it just zips in and attacks the carbon. That's why it happens so fast. But the thermodynamic product takes a little bit more effort, because what happens? Let's see here. I don't have, let's draw it out here. Okay. What now has to happen is, okay, if we want the thermodynamic product, then this chloride has to travel over here. And when it travels over here, then it can attack at the 4 position. So it just takes more effort and more time to get that chloride to move over to where the 4th carbon is, so it can attack there. This slide is highlighting the fact that disubstituted alkenes are more stable than monosubstituted. I already talked about that. Do you recall from Orgo 1 why that is the case? I'll tell you the one-word answer. Hyperconjugation. Does that spark a memory? Do you remember hyperconjugation? Well, that's the answer. So if you don't recall what hyperconjugation is, I would highly recommend that you go back to the textbook and refresh yourself on that. But that's the reason why that is more stable. Okay? So in summary, we can make out the general rules here. Okay? The general rule is the 1,2 product is going to give us the kinetic product. And the 1,4 product typically is the thermodynamic product. Okay. That is a general rule. There's going to be some exceptions to that, which we will discuss in class. But generally speaking, the 1,2 product is the kinetic, the 1,4 is the thermodynamic product. Okay, so if you just see a molecule like this, you can look at that and see that that is a 1,2, so you can assume that that is the kinetic product. Now, if you have 2 different products, how can you tell which one is going to be the major product between these 2? Well, you have to look at the reaction conditions. If the reaction is done at a colder temperature, then the 1,2 product is the major product. If you're adding heat or doing it at room temperature, then the thermodynamic product is favored. Okay? So that is how you can decide which is going to be the major product. It's dependent upon temperature. Okay?